Alright, so first I'd like to thank everybody who responded to the survey. Seems like the class is going fairly well for most everyone who responded. A couple of suggestions that I was given was to go slower in the PowerPoint, which I will endeavor to do now, and also to provide more examples, which I have done. So thank you for that. Okay, so we're going to talk about chi-square tests and contingency tables. And parametric and non-parametric tests are what we do in inferential statistics. So far, all the statistical tests we've examined have been designed to test hypotheses about specific population parameters. Remember, parameter is to population as statistic is to sample. Because these tests all concern parameters and require assumptions about parameters, they are called parametric tests. Another general characteristic of parametric tests is that they require a numerical score for each individual in the sample. But often researchers are confronted with experimental situations that do not conform to the requirements of parametric tests. In these situations, it may not be appropriate to use a parametric test. So, for example, when the assumptions of a test are violated, the test may lead to an erroneous interpretation. There are several hypothesis testing techniques that provide alternatives to parametric tests, and those are called non-parametric tests. Now, in this chapter, they've done chi-square, goodness of fit, and test of independence, and Fisher's exact test, and Mcnamara's test. They are non-parametric tests. But then there's another chapter, chapter 13, that covers all the rest of the non-parametric, not all of them, but most of the rest that the book is going to deal with, non-parametric tests. So that chapter is called non-parametric tests, but these are also non-parametric tests that I'm going to cover in this chapter. Occasionally you have a choice between using a parametric and a non-parametric test. If you have a choice, it's better to go with the parametric test, because it's more likely to detect a real difference or a real relationship. However, there are situations in which transforming scores into categories might be a better choice. So it may be simpler to obtain category measurements, high, medium, and low, for example, than to go and find out everyone's individual income, for example. The original scores may violate some of the basic assumptions that underline certain statistical procedures. So the chi-square test for the goodness of fit uses sample data to test hypotheses about the shape or proportion of a population. The test determines how well the obtained sample proportions fit the population proportions specified by the null hypothesis. I will give you examples of what that means. But how is this similar to a test we've already learned? The one sample t-test, that very first test we did, uses a sample to test a hypothesis about one parameter. Does my group mean, is it higher or lower than some hypothesized mean? This chi-square goodness of fit is similar to that. It's also known as the one sample case. It indicates whether or not the observed frequencies are a good fit to the expected frequencies. There is one variable that contains two or more categories. The observed frequencies are obtained through data collection, and the expected frequencies are given. Data is measured at the categorical, nominal, or ordinal level. So the null hypothesis could be either that there is no difference in proportions. This is used in situations in which a researcher wants to determine whether the proportions differ from one category to another, or no difference from a known population. So this is used when a specific population distribution is already known. For example, if it's known that 28% of licensed drivers are younger than 30 years old, so 72% are older than 30, or 50% of the population is male and 50% of the population is female. So the observed frequency is actually the number of individuals from the sample who are classified in a particular category. Each individual is counted in one and only one category. The expected frequency is the frequency value that is predicted from the proportions in the null hypothesis and the sample size. The expected frequencies define an ideal hypothetical sample distribution that would be obtained if the sample proportions were in perfect agreement with the proportions specified in the null. So if we said that the expected frequency of males and females in the population is 50 and 50, 50%, 50%. That is what, and we find it would be in perfect agreement with the proportions specified in the null. Okay, so how do you find chi-square? The computer is going to do this for us, but you'll see this in the book, and I want to explain to you what this means. First of all, this x is a Greek letter chi. When you square it, if you square root it, you get a z-score. When you square it, you get the chi-square. Okay, so how to find chi-square? This is kind of an intimidating looking calculation, but it's easier just to show you with reality. So what this means is this is the chi-square. X is, in Greek, the letter x is pronounced chi. So chi-square is the sum of the observed frequency minus the expected frequency squared divided by the expected frequency. So in order to just find, here's the observed frequency for each of these categories. We've got Democrats and gender, Democrat and male, Democrat and female, Republican and male, Republican and female. We've got 200 in our grand total, 100 in the column totals, and 85 and 115 for our row totals. To find the expected frequency, I would take my row total, which is 85, times the column total, which is 100, divided by the grand total, which I'd get is 42.5. What I usually do if I had to do this by hand is I would make a little slash here, and I would put the expected frequency. I'd do it for this one, and this one, and this one, and then I would say 25 minus 42.5 squared divided by 25, write that value down. 60 divided by whatever I wrote down here, squared, divided by the expected frequency, the overall grand total, and write that down. And then you sum them, and that's your chi-square value. Here, your degrees of freedom, it's your row, the number of rows, so we have 2 minus 1, and the number of columns. So I should have said rows like this. The number of rows is 2, and the number of columns is like this. So 2 minus 2 is 1. 1 times 1 is 1. So our degrees of freedom for a 2 by 2 table is 1. Okay, that's more information than you need, but if you were curious as to how you get these expected frequencies, I wanted you to see that. We're going to let the computer do that for us. Note, the formula for chi-square involves adding squared values, so you can never have a negative. All chi-square values are 0 or larger. When the null is true, we expect the chi-square values to be small. And then the bigger the difference is between the observed and the expected, the larger the chi-square value and the more chance that it will be significant. We don't have the row variable. We're just comparing some categorical variable against some hypothesized distribution. So it's just C minus 1, where C is the number of categories that you're comparing. So how would you describe this distribution? This is, remember back in the day, this is a right skewed, and over here this is the critical region. Alright, so just a really brief side note, in probability theory and statistics, chi-square distribution with k degrees of freedom is the distribution of a sum of squares of k independent standard normal random variables. The chi-square distribution is a special case of the gamma distribution, and is one of the most widely used probability distributions in inferential statistics. And I just wanted to show this slide because as your sample size increases, what happens? What does it start to look more like? Normal, right? Which is one of the reasons why the central limit theorem works on such a skewed distribution. And again, larger sample sizes are better. Let's do an example on page 506. This is example 1. I'm just going to read this out to you. A random sample of 100 weights of Californians is obtained, and the last digit of those weights are summarized here in table 11.2. When obtaining weights of subjects, it's important to actually measure their weights instead of asking them to report their weights. By analyzing the last digit of weights, researchers can verify that they were obtained through actual measurements instead of being reported. When people report weights, they tend to round down, and they often round way down. I'll summarize a little bit. Reported weights tend to have many last digits that consist of 0 or 5. In contrast, if people are actually weighed, the weights tend to have last digits that are uniformly distributed, with 1, 2, 3, 4, 5, 6, 7, 8, 9, all occurring with roughly the same frequencies. 0, 1, 2, 3, 4, all the way to 9. We could subjectively examine the frequencies in table 11.2 to see that the digits of 0 and 5 do seem to occur much more often than the other digits, but we will proceed with the formal hypothesis test to reinforce that subjective conclusion. So the claim is that the sample is from a population of weights in which the last digits do not occur with the same frequency. Based on the results, what can we conclude about the procedure used to obtain the weights? So let's do it. Our the null hypothesis is that all probabilities are equal. So that's 10%, 10%, 10%, 10% for all of these. And then the alternate hypothesis is that at least one probability is not equal. So all we have to do is we go into SPSS and we're going to go from 0 to 9, and we're going to load in the frequencies, 46, 1, 2, 3, 3, etc. Then we're going to enter the data in 2 columns like I've done. So last digit is the nominal variable. We don't need to give it a variable label because each of these is a category in its own right, you know. Then we weight the cases by frequency. So we go into data, and then we go down to weight cases down at the bottom. We have both variables here. We click weight cases by frequency, hit OK. Then we're going to go to analyze, non-parametric tests, 1 sample. All right, when you get the dialog box, this will come up and this guy will be checked. You have to check this one and say, we're going to customize analysis. For 1 sample, you could really let the computer do it, but sometimes it messes up. So it's best to do it by hand. So we're going to say customize analysis, and then we're going to click on this tab. This goes to fields. Both of these variables will be here, and we're going to bring the nominal variable over to the right into the test field. Okay, then we're going to click settings. Eventually we'll come back and click the run. While we're in settings, we're going to say customize tests, and it says compare observed probabilities to hypothesized chi-square test. We're going to click options. This one is automatically checked, and it would work if we did it this way, but I want to show you this way because we're going to use this consistently in the next one. So I wanted to show you how to do it. And it's better actually to do it by hand because you can make sure that the computer doesn't do something screwy. So click customize test, click the compare observed probabilities to the hypothesize, and then we're going to click options. And then we're going to say all categories have equal probability. This is already collect for us, we're going to leave it. The next example, we're going to click this guy. And then we'll say OK, and then we go back to that run. Alright, then it tells you what to do. It tells us, we don't have to even think about the p is low, the null must go. It says reject the null hypothesis because that p-value is tiny. Alright, we can come down here and we see our n sample size was 100. Our test statistic was 181.5. Our degrees of freedom are given to us, 8. And then the p-value is very, very small. So we can say we're going to state we stated our null and our alternate. Now we're going to state our conclusion. We ran the test. Now we're going to state our conclusion. The results of the test indicate that the probabilities are not equal. Chi-square, and then you write the degrees of freedom first, comma, n equals whatever your sample size is. Then you say equals and whatever the chi-square value was. P is less than 0.01. But we have a measure of an effect size. And this guy is called phi, and it's a little f in Greek. And for the goodness of fit, in a 2x2 contingency table, phi, which is equivalent to the correlation coefficient r, is a measure of effect size. Phi is defined by this chi-square value over the sample size. Then you take the square root of it. Super, super simple to do. Whereas n is the number of observations, and just like in the Cohen's, there's kind of a guideline. 0.1 is considered small, 0.3 is considered medium, and 0.5 is a large effect. So we would write it out. The results of the test indicate that the probabilities are not equal, and then we'd say phi is equal to 1.81. And you can go here and use that as a phi calculator, effect size calculator. And it also just gives us some pretty values. It gives us the observed and hypothesized values and a bar chart of your own data. So you can see that the observed of 0 and of 5 are super big, so I would say that these are not measured weights, these are self-reported weights. Okay, so let's do a different one. We're on page 508. And this is kind of a weird one. According to Binford's law, a variety of different data sets include numbers with leading first digits that follow the distribution shown in the first two rows of this table. Data sets that tend to follow Binford's law include a class of errors in clinical trials, as well as magnitudes of gradients from magnetic resonance imaging, those MRI scans, computed tomography CT scans, and ultrasound images. The bottom row lists the frequencies of the leading digits of the magnitudes of gradients from an ultrasound image. Do the frequencies of leading digits in the bottom row appear to fit the distribution of Binford's law, as expected, or does it appear that the image has been corrupted with a substantial amount of noise because the leading digits do not fit the distribution of Binford's law? Okay, so what we're going to do is we're going to take these data and do the same thing, but now we're going to, instead of just letting the computer say all of them are equal, we're going to actually manually enter these probabilities. Okay, so when we enter the data, we have the leading digit, 1, 2, 3, 4, 5, 6, 7, 8, 9. We've got the frequency here, and then we've got the probabilities, right? So 30.1, we enter it as 0.301, 17.6, 0.176, and so on. I put this column in because it makes it much easier for your data set. Even if you save it and come back to it later, you already have this. You don't have it written on some scrap of paper somewhere. So I put it in, and then it makes it easier to load the data into the SPSS interface when it's time to do the thing, and I'll show you what I mean by that. Okay, so because of that, you want to stay in the data screen. So you can do your stats from the output screen or the data screen. Stay in the data screen like I've done here. You can see the numbers back there. Go to Analyze, Non-Parametric Test, One Sample. You're going to follow all those same steps as the previous. You're going to get that first tab, second tab. I can go back and show you. You're going to go Customize, then we'll go to Fields. You're going to go to Customize and then hit Options. And then instead of that, you're going to click Customize Expected Probability. And when you do that, you're going to get Category 1, which is here. And I just highlighted the first two, but I really mean to highlight all of them because you're going to load them all in. So you say 1, and the frequency is 0.301, and then 2, and the frequency is 0.176, and 3, etc., all the way down. You click OK, and then you click Run. Alright, so when we do that, we evaluate our output. I've just put it all on the same page here. So it tells us what decision to make. We're going to retain the null hypothesis. I've covered up my sig, but it's also down here, 0.186. So it's not less than 0.05. So it is, sorry, not significant. We fail to reject the null and conclude that there is not enough evidence to warrant rejection of the claim that the 271 leading digits fit the distribution given by Binford's law, and there isn't enough evidence that the ultrasound readings have been corrupted with noise. Okay, so, and here we write out our chi-square. I didn't do the phi coefficient for this one, and that's okay. Okay, so the next test is chi-square test of independence. So where the goodness of fit is testing one sample against some sort of hypothesized proportions or predetermined proportions, the chi-square test of independence is a little bit different. It determines whether there is an association between categorical variables, whether the variables are independent or related. It's also a non-parametric test. It's also known as the chi-square test of association. This test utilizes a contingency table to analyze the data. A contingency table, also known as crosstabulation, or two-way table, is an arrangement in which data is classified according to two categorical variables. The categories for one variable appear in the rows, and the categories for the other variable appear in the columns. Each variable must have two or more categories. Each cell reflects the total count of cases for a specific pair of categories. It's easier to see than to say. Okay, so the chi-square test of independence is commonly used to test the following: statistical independence or association between two or more categorical variables. The chi-square test of independence can only compare categorical variables. Okay, so it's categories, the nominal variable. It cannot make comparisons between continuous variables or between categorical and continuous variables. Additionally, the chi-square test of independence only assesses associations. It can't provide causation or any inference about causation. It's just like correlation. Correlation doesn't imply causation, neither does association. If your categorical variables represent pre-test and post-test, then the chi-square test of independence is not appropriate. This is because of the assumption of independence of observations is violated. In this situation, we're going to use Mcnamara's test, and I'll show you what that is, but it's only appropriate for dichotomous variables. In Chapter 13, we'll cover a different technique to do that. Okay, so what have I said so far? We've done a goodness of fit test, which compares one group to some sort of hypothesized proportions. Now we're looking at two sets of categorical variables, so gender and political party, right? Like that table I showed you earlier. Is there an association between gender and political party? We're going to do one from the book, but it's two categorical variables, two or more categories or groups for each variable. So I could do gender and political party and do Democrat, Republican, and independent. I can have one with 2 and one with 3. I can have one with 3 and one with 4. It doesn't matter. The independence of, so the requirements are that we have 2 or more categories. They're independent observations. There's no relationships between the subjects in any way. They're not paired. And that we have a relatively large sample size. The expected frequencies for each cell are at least 1. And the expected frequencies should be at least 5 for at least 80% of the cells. We're not going to worry about that. The computer will tell us. All right, so let's look at the hypothesis. The null hypothesis and the alternative hypothesis of the chi-square test of independence can be expressed as variable 1 is not associated with variable 2, or variable 1 is associated with variable 2. So how is this like what we've already learned? Because it evaluates the independence between populations represented by 2 independent samples, it's somewhat like an independent samples t-test, and because it tests association between variables, it's also somewhat like correlation. Alright, so here's the test statistic, and that's the fancy way of writing it out. And I showed you how to calculate the expected frequencies. This is the sum of the rows, sum of the columns, and this is just O minus E squared over E squared, right? It's just the statistical way to write it out. We don't need to worry about that. The computer will give us the... Alright, so your data setup. There are 2 different ways in which your data may be set up initially. The format of the data will determine how to proceed with running the chi-square test of independence. At minimum, your data should include 2 categorical variables represented in columns that will be used in the analysis. The categorical variables must include at least 2 groups. Your data may be formatted either in either of the following ways. So this way, we have cases represent subjects, and each subject appears once in the data set. That is, each row represents an observation from a unique subject. The dataset contains at least 2 nominal categorical variables, string or numeric, and the categorical variables used in the test must have 2 or more categories. Okay, but what we're going to mostly use is the way we did with sensitivity and specificity, and like we've done with the ones I've showed you before, because most of our data will come and it will be in a contingency table, and you don't want to have to go and write out, hundreds of lines of for each individual person in that contingency table. So we're going to do it this way. Each row in the data set represents a distinct combination of the categories. The value in the frequency column for a given row is the number of unique subjects with that combination of categories. You should have 3 variables, at least. 1 representing each category and a 3rd representing the number of occurrences of that particular combination of factors. Don't forget, you have to weight the cases, right, by the frequency. We've seen this before. This is not news. Okay, so the research question. Is there an association between gender and smoking? So the null, there is no association between gender and smoking. And the alternate, there is an association between gender and smoking. So I would go to Analyze, Descriptive Statistics, Crosstabs. I'm not going to show you that because we've done that many times. You're going to move smoking to the rows and gender to the columns. You're going to check the display, down here, check display clustered bar charts. Then you're going to click on Statistics and it'll make this thing pop up. Click chi-square, hit continue. Now click cells, and you're going to have this one already highlighted, this observed, so you're going to click expected and row, and that's it. And then you're going to click continue and then go back and click OK. You're going to get output, and you can see here we have males and females, so the boys are blue and the girls are red, and they across non-smoker, past smoker, and current smoker are fairly close. This one's a little bit iffy, but they show consistency between the genders across the 3 levels of smoking, indicating that we probably won't see an association. But let's check the output. So we can see here, here's my sig, asymptotic sig. It's 0.205, which is larger than 0.05, so we reject the null. We have 2 degrees of freedom in our N. We're going to need this to write the results in the next slide. So we fail to reject the null. There is no association between gender and smoking for those data. If there were associations, we could further see where the differences were between expected and observed, right? So here's my expected count was 142 and I found 149. My expected was 154 and I found 148. I was expecting 18 and I found 13. I was expecting 19 and I found 24, etc. These are all really darn close, so that's why we don't have significance. So the results indicate that there is no significant association between smoking and gender, and we write it out, where degrees of freedom and the sample size. And then for a test of independence, we have a different type of effect size, Kramer's V. It's calculated as the square root of the chi-square over the multiplied n times the degrees of freedom, and you can't really see it here, but I have 2 little stars, and what I mean by that is that you look at your degrees of freedom and you say number of rows and number of columns, rows minus 1, columns minus 1, but here we mean the smaller of those 2 values, and so that's just beyond complicated. So we're just going to use a calculator, but it's not just your regular degrees of freedom. Alright, so we go to the website here, we pull it up, we have to input that we had 3 rows and 2 columns. It will give us this highlighted, these highlighted cells. We go back to our contingency table and type in the observed frequencies, type them in, click calculate, and we get the same input, same output that we've got from SPSS. We got a 3.17, 2 degrees of freedom, our p-value is 0.20, and our Kramer's V is 0.08. So even though it doesn't make sense to find the effect size for a non-significant finding, we would have said this is a small effect size because I have 2 degrees of freedom, slide across, 0.8 is closer to small, 0.08 is closer to small than it is to medium, so we would say it is a small effect. Alright, so let's do another one. There's a research question, is there an association between living on campus and class rank? The null is that there is no association between living on campus and class rank, and by that I mean freshman, sophomore, junior, senior. And the alternate is there is an association between living on campus and class rank. For this, we all do the same check boxes, put the rank up or under in the rows and the live on campus in the columns. Okay, and I'm just saying that because that's the names of the variables. So we evaluate our output. I can see that underclassmen, so those freshmen and sophomores, fewer live off campus than live on campus. And the upperclassmen, fewer live on campus than off campus. So there appears to be an association between upperclassmen and the lowerclassmen groups and whether or not they live on or off campus. This shows the differences between the 2 groups over the level of on-off campus. Okay, so we're going to look at our 2x2 table. Because this is a 2x2 table, we get a little more output, namely Fisher's exact test, which gives you the p-value alone. We see there is a significant association between rank and on and off campus. So here's my significance, 0.000, so 0.01. Degrees of freedom is 1, and our sample size is 388. So we state the conclusion. The results indicate that there is a significant association between rank and on-off campus, and I report it out that way. Now I'm not going to go through all the phi coefficients and Cramer's V's and all that, and I'm just going to kind of sail through Fisher's and Mcnamara's for your information. I'm not going to ask you to do this in the homework. I know there's an awful lot of statistics coming at you in a short amount of time, and I don't want you to walk away without having the information. But I don't expect you to memorize it. I certainly don't memorize it. If I have to run a Fisher's exact test, I have to go Google it myself. Okay, so now we have a chi-square test of homogeneity. It is the same test as the test of independence, but it's just a semantic difference. Instead of testing the independence between the row and the column, we are testing the hypothesis that the different populations have the same proportion of some characteristic. For example, this TOH is test of homogeneity. In a study of eating habits of children, a nutritionist selects a random sample of 300 first graders, 150 boys and 150 girls. Each child is asked how many times they eat fast food, 1 time a week, 2 times a week, or 3 or more times a week. So the null would be that the proportions for each choice are the same between boys and girls, and the alternate would be at least one is different. If I give you the results and say chi-square value of 2, n is equal to 300, I get this big chi-square value and p is less than 0.01, we would conclude that the proportions for each choice are not the same for boys and girls. Alright, then they talk about the Fisher's exact test. And I have this little thing over here. It says Google lady tasting tea experiment. And that is where Ronald Fisher got the idea for this. And this Fisher's exact test has been used for many, many things. But it came from his secretary tasting tea. I won't tell the story. You can Google it if you're interested. Okay, so this is strictly for a 2x2 table when one cell has less than 5 expected frequencies. So it's for tiny sample sizes. This test will give you an exact p-value. And it's a very complicated calculation, but the computer will do it for us in no time. So example 3 on page 520, test the question whether people exposed to yawning make someone yawn. With these data, we run a crosstabs just like usual, but we look at Fisher's results and we find that there's not enough evidence to reject the null. So we come over here and we see this p is equal to 0.51. That's not smaller than 0.05, so we reject the null. Looking at if you see someone yawn, we don't have enough evidence that shows that in the sample of however many people we had, let's see, 50 people, there weren't enough people that were caused to yawn different than chance alone. Okay, and then finally, the Mcnamara's test for matched pairs. This is used when we have matched pairs. So this is kind of like the paired samples t-test, right? This is used when we have matched pairs for like a pre-test or a post-test, or when the samples are related, like a left ear measurement and a right ear measurement, for example. But the variables in both rows and columns are dichotomous. So for this left ear and right ear, it would be pass-fail, and same for the pre-test, post-test, because they have to be dichotomous. You go to Analyze Descriptives, Crosstabs, put the pre-test in the row and post-test in the column. Right? We do the same thing. We have to weight the cases, do all of that the same way. Here we're looking at whether or not you wear a hip protector, and if you wear it, whether or not you have a fracture. So no hip fracture without the protector, and with the protector. And so we put those data in, we run the results, we run the test, and we can see the results are not significant. So the proportion of hip fractures with the protectors worn is not significantly different than those without the protector worn. So we would start here. This is Mcnamara. We would go, when we go Analyze Descriptive Statistics, Crosstabs, we click chi-square, and then we're just going to click Mcnamara down here. All right. If you do it with just the chi-square, you're going to get all of these data, but you don't get the Mcnamara. If you click Mcnamara, you're going to get all of these data plus the Mcnamara test. Okay, so if you just have Mcnamara and not chi-square test, this is all you get, the Mcnamara test. So I like to check them both, chi-square and Mcnamara, so you get everything. More information than is needed. Okay, so more on non-parametric statistics. I know that was a lot of information, and I don't expect you to memorize it in any way, shape, or form. I just want you to know that there is a whole host of non-parametric statistics, and you're going to find out of more of them even in the next chapter that we cover, chapter 13. And just that there are those that are out there. So if you end up with a data set where you have a small sample size and you think, oh darn, I can't do anything with this, look to non-parametrics. If you have a data set where you violate some assumptions, look to non-parametric statistics. If you can't remember which one it is, just ask Google, and I guarantee many people will have answered it. So non-parametric statistics, they're not as robust, they're not as, there's nothing wrong with them, but if you can do the parametric, do that first. If you can't, then do the non-parametric. I published a paper where I've done both. So it violated assumptions. I did the non-parametric, and then I ran the parametric and showed that I got significance in both instances, and it made the editors happy, and I got it published. So just know that there are many non-parametric options, and if you can't do the parametric stat, then look to the non-parametric. So like I say here, this is like a restaurant menu of different tests you could do when you have different perspectives on questions regarding the independence or associations between categorical variables. I don't even remember how to calculate them all in SPSS when I'm doing my own research. My intention here is to give you a reference to use when or if you need to do these tests. I Google a lot, and when I have to do an obscure test, I sometimes forget which one is which. I'm not lying. I just, I don't always memorize these things, and so I have to go and check. So in the next chapter, we're going to cover another menu of non-parametric equivalents of parametric tests that we have learned so far. Okay.